Welcome to the Deep Dive. This is where we help you get quickly up to speed, especially if you're a number theory student exploring the amazing online encyclopedia of integer sequences, the OEI.
It's an incredible resource,
Yeah.
a real universe of numbers.
Absolutely. And today we're diving into one specific sequence, A000281. The description is expansion of cos x, cos 2x.
Right. Seems simple enough on the surface, cos over cos 2x, but the sequence it generates.
Yeah.
That's where things get interesting.
Let's unpack that. So we look at A000281, and the first few terms we see are 1, then 3, then quite a jump to 57, then 250,737. They grow fast.
They really do.
What's the mechanism here? How are these specific integers being generated?
Well, it all comes down to the Taylor series for that function, cos x 2x. You know, how you can represent functions as these infinite sums of polynomial terms.
Right, like breaking it down into simpler building blocks.
Exactly. So the sequence term an is defined using the coefficient of x to the power of 2n in that Taylor series. But there's a twist. You take that coefficient and you multiply it by 2n factorial. That's 2n factorial.
Ah, so that factorial is what's making these numbers whole integers and making them grow so quickly.
Precisely. Without that factorial, you just have fractions. It's this scaling factor that reveals the integer sequence hidden within the trigonometric function.
Okay, that makes sense. Can you maybe walk us through an example? How does the expansion actually lead to, say, the number 3 or 57?
Sure. So the Taylor series for cos x starts out 1 plus 32 by 2 plus 198 by 4 plus 3780 by 6 and so on.
Got it.
So for the first term, n0, the coefficient of x0 is 1, and 20 is 0, which is 1. So 1 times 1 is 1. That's a0.
Okay, straightforward.
Now for n1, we look at the by 2 term. Coefficient is 32.
Right.
We multiply by 21, which is 2, or 2. So 32 times 2 gives you 3. That's a1.
And for 57, that must be n2.
Exactly. The coefficient of by 4 is 198. You multiply by 22, which is 4, or 24.
Okay, 198 times 24. Let's
That's
see.
it.
8 goes into 24 3 times. 19 times 3 is 57. There it is.
You got it. A really elegant connection between, trigonometry and these integer sequences.
It really is. But this sequence, it feels like it's more than just a neat calculation. Does it have deeper roots, mathematically speaking, a history?
Oh, absolutely. This isn't some obscure sequence cooked up recently. It actually goes back quite a way.
Yeah.
J.W.L. Gleicher studied it back in 1914.
Wow, over a century ago.
Yes. And of course, Neil Sloan included it in his original handbook, which was the precursor to the OEIS. So it's foundational in a way.
Does it connect to other areas? You often find these sequences popping up in unexpected places.
You certainly do with this one. It has connections to some pretty fundamental concepts, things like Euler and Bernoulli polynomials, which are cornerstones in number theory and analysis.
Okay, so core mathematical objects.
Right. And it even relates to the generalized Riemann zeta function. Plus, you find representations of it using continued fractions, which adds another layer of elegance. It really threads through quite a bit of mathematics.
That's fascinating. A simple-looking ratio of cosines leads to all that. Now, you mentioned how quickly the terms grow. I saw a note about approximating large terms.
Ah, yes, the asymptotics. That's another really striking feature.
So how well can we predict these huge numbers?
Extraordinarily well. Take, for example, A250. The 250th term, it's a massive number, something like 10 to the power of 1181.
Unimaginably large.
Right. But there's an asymptotic formula, one developed by Simon Plouffe, that gives an approximation. And for a 250, this formula is accurate to 238 digits.
238 digits. For a number that large, that's incredible precision.
It truly is. It just highlights the deep structure and, the hidden order that exists within these sequences, even when the numbers themselves become astronomical.
So we've gone from this cos 2x definition, seen the Taylor series connection, touched on its history with Gleicher and Sloan, its links to major mathematical ideas, and ended up with this almost unbelievable asymptotic precision.
It's quite a journey for one sequence.
It really is.
And it makes you think, doesn't it? Understanding these connections is key. You start with something familiar, like cosine functions, and it unfolds into this complex, interconnected world of integers and high-level mathematics.
A good reminder that there's depth everywhere in math.
Exactly. It poses the question for you, the listener. What other functions, maybe even simpler ones you work with, could be holding similar secrets? What integer sequences might they generate if you look closely?
That's a great thought to end on. Keep exploring those patterns. We'll see you on the next deep dive.